So there was a quiz on Crookes radiometer. Did you guys get a chance to work on that? Okay, you guys forget. Okay, that's fine.
Yeah, we can submit next class.
What about 4:30 before 4:30?
Yeah.
Something like that. Did I?
Yeah.
Yeah, remember it's a quiz. You just have to
Yeah.
spend a little time on it. Okay. Okay, we did the idea of conservation, or we introduced two conservation principles, or three now, right? Three, yeah. So it comes charge, energy, and momentum. And now we want to really use them in some place. And the momentum equation basically is a force. It can be used to calculate the pressure on a medium. It's kind of a nice interpretation. So before that, I should say homework, right? So homework 2 is due on Tuesday. So
February 1.
yeah, February 1. That's correct. So based on whatever we do today, it should be very useful for what you will do in your homework. Interpretation wise, the problem is entirely different. So it's not that you'll be able to use exactly the same results, but the spirit or the concepts will be very awesome. So, and when is the exam? Let's prepare that also. Keep
February 15.
Tuesday plus 14. Okay, so let me begin by putting down the equations, the conservation principles of conservation laws. So there is conservation of charge. And in this way of writing, then I don't have to refer to the Maxwell's equations again. So it's kind of, this becomes your basic setup. In fact, that should be put up as an exercise, right? Let's say quiz, right? So here's a quiz. I mean, I just thought about it now. Okay. So this is a quiz. So we derived 3 conservation laws, right? So the conservation of energy, conservation of momentum, and conservation of charge from the Maxwell's equations. Can you do the reverse? Like, is it possible that these 3 equations are fundamental and Maxwell's equations are derived? Right? So then you don't have to call Maxwell's equation, then you just say conservation principle. So it might be possible, but I never thought about it before, so I never attempted on it. So it's a quiz problem, so just think about it and give it a shot. Is that clear, Christian? Yeah. Right, so can you do the reverse, right, starting from here? Can you get that? It is pretty much practically reversing your steps, but maybe it's not unique. That's a possibility. Okay, with that, let's go. So this is charge density and current density. That's clear. And in this way of interpretation, you also say that current density is the flux of charge density. That the flux is the idea of flux in hydrodynamics, not the idea of flux in the electrostatics causes. Then we have conservation of electromagnetic energy. And that says that change in energy density plus the divergence of the flux of energy density, which we say is the Poynting vector, plus the dissipation of energy into motion, the mechanical motion. It's given by J denoted with E is equal to 0. One could ask, why is there not a magnetic field, but magnetic field you don't lose, or magnetic field cannot move things like cannot increase the kinetic energy, or the dissipation does not happen. Yeah, one should be careful stating that. So here I should define my U and S. Let me say, put it here. So U is 1/2 P with E plus 1/2 P H. And S is the flux of energy density. That's the best way of saying it, but it's also called Poynting vector. It is E crossed with H. All this are precision and time dependent. Then you have conservation of momentum or electromagnetic. That is time derivative of momentum density, electromagnetic momentum density now, plus the divergence of whatever we write is going to be the flux of the momentum density, but momentum is a vector. When it was a scalar, it became a vector, right? Because you need the divergence of that quantity, so you need a vector if it's a scalar, but if it's a vector, then it becomes a tensor, right? Whatever, because you have to take one index off, right? So it becomes a tensor now. So this is the flux of energy. Sorry, flux of energy, flux of momentum density. And whatever is, how do you actually lose momentum? By exerting a force on a charge, right? Instead of having the force on the medium itself, it can be on the charges. So this is the force density on charges. On the here there is a charge there. Here there's a dissipation of charge. Here force acting on the charge has to be always equal to this. This calls for definition of G and T. G is very closely related to S. So G is simply D crossed with D, which is nothing but 1 over C square times S. That's E crossed with. So remember D and E. Or D and B are related to E and H. And everything is in vacuum, right? With the point charges, so we're not really putting in a medium in. That leaves us with one definition here, which is the energy, which is called the energy momentum tensor, or the flux of momentum density. And that's a tensor. It's equal to tensor, so it's diagonal elements are just the energy itself, energy density. That's here U, but then there's also non-diagonal terms, which is D and E. Very similar to the energy, but now there is no dot product here. Minus B. Wait a second, no dot product is an out product. Okay, so that's sort of the review of whatever we had until now. And now let's see how this works, kind of, or how do we interpret these things. So let's try to use the third equation and see if we can learn something about a known system using this. Let's do an example. An example will be that of a planar surface. Let's consider as capacitor. So let's consider a capacitor. So let's say this is capacitor. It has the plates are of infinite extent. That's your capacitor. And let's say this is positively charged. So negatively charged. And the electric field in that case would be going here, right? That's your description. That's your electric field. And it's a static capacitor, nothing is happening. So magnetic field is zero. So let's see this. So what is the, as far as electric field goes, how does it work? Electric field is equal to, okay, and this, let's say, is Z equal to 0, and this is equal to Z equal to A, and which means that this is Z direction, that direction. So that's all, making it more precise. And in that case, the electric field can be said to be Z hat times. So I need to have some. So what's the electric field inside a capacitor? What is the information I need for this? Is it stronger closer to the plate or in between? Where is the electric field the strongest? Is it at the center of the plate or to the closer to the plates? Closer?
At the edges.
Should be?
At the edges or something.
At the edges. This is of infinite extent, right? Maybe I should clarify. So everywhere it's the same, right? As I go up, there is no edge there. But maybe what you mean by edge is here, close.
Yeah, close.
So as you get closer, it will be stronger. So if it is stronger, then maybe I should show it like this. Like if I have a positive charge, right? This is your electric field lines, right? Agreed? And is the electric field stronger on this side or that side? Here, yeah. It's stronger here. So it will be stronger here, right? 1 over R square, right? As you get smaller, R gets smaller and smaller, electric field gets larger and larger. Visually, how do I know that? There is something called electric field lines. There is some properties of electric field lines. Electric field lines represents the electric field, right? This is the direction of the electric field. How do I know the magnitude of the electric field? From this diagram. If I don't tell you what exactly Q is. What information in electric field lines gives me the strength of the electric field? Is the question clear?
Number of field lines.
Number of field lines per unit volume.
Yes.
Right. So have a small box if you want. So I think in this case it is good to do this. Right. Have fixed number of lines and then have a box here and I have a box here. Right. Here or there. You can move around. There are more number of lines there. That's what gives me that information. So it's very clear that as I get closer and closer per unit volume, I'll have more number of lines, right? So if the now answer again, this, where is it stronger? This way, that way?
Same.
It's the same. Right? So electric field does not change inside a capacitor, it's constant. Right? You have uniform gravity on the surface of Earth because it is flat. Right? So same thing, this is a sphere. If I make this bigger and bigger on the surface, it becomes flat. Right? That's flat. It's a flat on flat Earth, we will have constant gravity. Right? So we are presuming that our Earth is flat when we say it's 9.8 meters per second. Same thing here. This flat surface is equivalent to saying it's a very large radius sphere. So electric field is constant. So if it's a constant, it doesn't matter whether I'm here, here, here. I can get as close as I want to the surface. In fact, I can touch the surface and still it is constant. Okay. So it's a constant, then what does it depend on? It doesn't depend on distance. So what does it depend on? So it depends on the charge, right? So it depends only on the charge. How much charge is there on a plate? Is it finite or infinite? On an infinite extent of plate, there will be infinite charge, but then the area is also infinite. So charge per unit area is finite. Charge is infinite, area is infinite, but charge per unit area can be finite. And that we will say sigma, right? Typically we say sigma is charge per unit area. Q over A, but forget about Q over A, let's say sigma, and it is sigma. That's all it depends on, except a constant also, that's epsilon naught. So very simple expression for an electric field inside a capacitor. It depends only on the charge density. It's like 9.8 meters per second squared. It doesn't depend on anything. If you fix the planet, it depends on the mass and radius. That's it. That's the electric field inside of this. So I have to say that this is Z is less than A and greater than 0, and it is 0 otherwise. And what about the magnetic field? This is a capacitor. Let's not make it move. Let's not move it around. Let's say it is just 0. Okay. So that's the configuration we want to work with. And this is our force equation. And let's see what we would like to know. What's the force acting on a plate, right? So we know that this plate will attract this plate, right? And that means there will be pressure on it. So it tries to pull each other. But typically you would say that, how would you do that force? There is an electric field exerted by this on that. So this positive charge will attract this positive charge will attract that. Each charge here gets attracted, and each of the charge pulls that. So you can do Coulomb's law and get that. But we won't use that. We will try to use this equation. All right. Now we have a new machinery. So let's try to do this. You know that this is the force density. If I use the right volume, I might be able to get the same information. So let's start with this. And before that, let me calculate GT, or let me first have a strategy how to go, and then we will go around. So strategy would be that I want to calculate the force on the left plate. So I need a volume now, right? So let's say, so this is a plate. So I just need to talk about a volume. So I choose this to be the volume. Okay, and in fact, I can take this infinite extent. This is a volume in the sense this is a cube or it's a cylinder. Right? This could be circular or this could be flat, and I can extend this. Is that clear? That's the volume cuboid in here. And I can say, let's say this is delta. So this is plus delta, and this is minus delta. It doesn't have to be 0. delta could be large or small. I just chose delta, but if you make it small, then you are enclosing the plate completely. So that's going to be our equation. Before we do anything, it is actually simple to see that if E and B is 0, then G is immediately 0. Right? Momentum density is 0 because it's static. Electric fields are not moving. At 0, G is S is E cross H. H magnetic field is 0. So that's 0. Okay. So that's right away gone. So force density is, there's only 2 equations remaining. So I have divergence of the flux of momentum plus force is equal to 0. So let me write this as force density is minus of this. Okay. I'm interested in the force on the whole plate on the left. So integrate over this volume. So force, total force, F total. This is the force. So force on the plate at Z equal to 0. That's equal to the volume that encloses that whole plate. So this is d cube R times the force density. And this volume is the volume enclosed by that cube. And I want to make that extend all the way to the top, extend all the way to the bottom. Right. And that can be specified better. The area of this whole plate, which is going to be infinite, so that's a constant, like that. Nothing is going to depend on that. Let me pull that out. Times dz, which depends from 0 minus delta, 0 plus delta of the force density. Is that clear? Or if you want, if you don't like this area yet, this is some dx dy. So this is d2, d2r, right? It is infinite. So that's basically area. The force will not depend on area because there is symmetry and then at each point there is an x-y dependence in there. Okay, clear? Yes.
What is the minus delta and plus delta again?
Oh, this was this point here. So this is z equal to 0. I am interested in calculate, this is a local equation, right? I would like to calculate the force on a volume. So I had to pick that volume. I pick the volume around the plate. So if the force is acting on that whole volume, where is it acting? It's on the plate. And I can take, if that is not comforting, because this is how it could be a by 2, take the limit delta tends to 0. So in the extreme limit, it is hugging that plate. Right? That volume is having only the plate inside. So whatever force is acting on that volume is acting on that plate. Right? So that's that. So total force on this left plate is the total force on a volume that on a volume V that encloses that plate. It doesn't have to be hugging, but I will choose it to be that. There will be simplifications in that. That's all. Even if you were to do this a by 2, it will come out the same because it's the same plate. That is, as far as that plate is immersed in that volume, it will experience that. And that's force density, and that can be written in this one. Is that clear? That question? Okay. So that's this. So as I argued, or let's go one more step. This is volume, right? So that's the same as, instead of talking about force in terms of this F itself, it is good to work with the fields, right? So I had to go to the field region. So that's the same volume V, but now minus d cube R times divergence of the flux of momentum. Like this is the analog of a dynamics that is coming in. We are interested in the force, but we won't calculate it using the force. We will calculate it using the acceleration. Like think of Newton's law. If you're interested in calculating the force, one way to do it is just measure the acceleration. Mass times acceleration has to be equal to the force. Here it is not mass times acceleration, it's the momentum and the flux of energy. There are two pieces in there. So instead of calculating the force itself, which we can do, that is what we do in electrodynamics course, that we will actually go and calculate this charge to charge, right? Charge is the central concept there. Here we don't want to do that. We want to go to the electric field. Electric field is a dynamical quantity here. So calculate using the electric field, and that's your electric field is inside and this. Clear? What's the motivation here? Question?
So motivation, can you repeat?
Yeah, so the motivation is, okay, now if I'm interested in the force, I can say, I'll go back to here, right? Here, when I say T, the energy is stored in the electric field. This is the electromagnetic momentum, right? Where is the energy stored? In the electric field, right? Where is the energy stored? In the electric field, which is spread out, which is everywhere in space. But what about this? F is the force acting on a charge. That is also okay. Either I can say this is a force or this is a force. If this is zero, these two are equal, right? So one way of calculating the force is from the electric field. Another way is from the charge. And they will be, it's like equal and opposite reaction forces, right? If this is true, that also. It's not really equal and opposite reaction forces. It's like dynamics, right? Force is equal to mass times acceleration. You can either calculate acceleration and tell me the force, or you can calculate it using the force itself. So here we are going to have the motivation that we are going to depend on the electric field. So here that is going to be the central piece. On the other hand, what do we do in elementary introductory physics course? We do charge to charge, right? Coulomb's law. This charge exerts a force on that charge. Right? That's the central idea. Electric field is not really necessary there. We can get away with the whole concept of electric field in Coulomb's law just by talking about force, right? Charge to charge. That's it. Here, what we are saying is that the whole information about the charge to charge force is there in the electric field that's permeating whole space around it. That's a deeper concept. We are saying electric field is the central point, and we are going to capture that, at least in the simple scenarios. These things get more harder when things are moving. And in fact, it remains unclear how all these things give you a consistent result when things are moving. You might have heard that, for example, if a capacitor is moving, then it can, since charges are now moving, right? If it is accelerating, then it can start radiating. And if that is radiating, there is a back reaction, and all these are not completely consistent with what we understand in terms of these equations. It's not completely understood. It is surprising. For example, here is the, again, it can be a quiz if you want. I said G is a momentum, right? Or this is the energy or momentum density, electromagnetic momentum. That's clear. So you would say that, okay, let me move a capacitor and I should be able to measure this momentum, right? If you have exactly, correct. But it turns out that it is not very clear what exactly is the momentum if there is a medium. Okay, so this is called Abraham Minkowski I think controversy, or Abraham Minkowski. Yeah, let's put it as controversy. It is a controversy in the sense, this is about 1900. Abraham said that the definition of the momentum is more related to the Poynting vector. And Minkowski said that it is D cross B. So Minkowski's definition of G is D cross B. It doesn't matter, these two doesn't really have any conflict if you're not in a medium. And that's why if you notice, I'm not really bringing any medium, right? There's a charge in between, there is no dielectric in it. I could have said that this is filled with a mica sheet. And then I asked, what is the momentum of it? And there is electric field inside mica sheet also. And then I can say, what is the electromagnetic energy, or momentum inside that medium. As of today, we do not know what is the definition. Half of the literature says this Minkowski is correct, but half of the literature says Abraham is there. There are lots of, and one would think that do an experiment. I mean, this doesn't require, like, precision is not an issue here. You can do these measurements, but as of today, it has not been settled. This remains an open question. What exactly is the momentum, electromagnetic momentum inside a medium? Primarily because when you're having time dependent, most of these things are frequency dependent. Like light oscillations are so fast that you cannot really get these speeds very clearly. That's my understanding. If we are lucky, we might have a talk based on this this semester. I'm trying to invite someone to give a talk because we have this virtual talks. It will be it is easy to invite our speakers, and he's an authority on this. He's written a review article on it. So hopefully we will get. He will agree to it, and then we will have a talk on it, at least a collection of thoughts of what has been done in the last 100 years and what is the challenge in this. So the point was, what was the motivation? The idea is to write it in terms of electric field, and it is still challenging. That's my point. But simple problems you can do, and I'm doing the simple things. Okay. So let's calculate this force. And again, force can be calculated this way or that way. We will use the left-hand side in this equation, which I'll move it to the right. So the force is equal to the divergence of this quantity here, which is written in terms of electric and magnetic field. But you see that this is a divergence of a volume, the same volume V. But whenever you have a divergence of a volume, it is only on the surface, right? So this is a derivative, so it survives only on the boundary. So using divergence theorem, we immediately say that this is a closed integral of, so I like to say that this is the surface enclosing that volume. So that's what this means. I think this was, I think one of you guys asked me this, that why V is there. So this is the closed surface enclosing the volume V. Right? That's a unique surface. And now it's a area vector, A dotted with T. This volume has two surfaces. If this is of infinite extent, this has two surfaces, one on this and one on that side. If you feel that, oh, that's not very correct, even at infinity, there is electric field, right? We are talking about an infinite extent plate, then electric field exists at an infinity there. But then this is the normal vector here is in this direction, correct? So electric field is in this direction, so it will never contribute. So these two surfaces do not contribute. Electric field is 0 on the left. Right? We are saying this is a conducting plate. Electric field is not there on that side. So we said here, right, electric field is 0 there on that side. So only on one surface it contributes. So that's all there is to that. So that's equal to minus. So let's say on the surface, how do you say this? So this is the A at, so this is Z hat, right? So on this side, it is the z hat direction, dotted with t. And this should be evaluated at z equal to 0 plus delta. At this point, you can notice that t, whatever it is constructed out of this. This doesn't have any area dependence, or this doesn't have any xy dependence. Like this is a constant here. So this will be constant. So this area will not do anything. It comes out. It's a separate piece altogether. Right? T does not have any xy dependence. This is an integral in x and y. This doesn't have any xy dependence. So this is a total area A, the area of the plates. So I can talk about force total per unit area as minus z hat dotted with t. So no integrations needed. T gives me that, and this is evaluated at z equal to 0 plus delta. Any questions? Yes.
I'm going from the closed surface of the volume dA to the regular interval dA. Actually, the one below that. Yeah, to there. That's because of the only contributing side is
One
right.
side.
It's one
In
side.
general, that should be 4, right? If it's a cylinder, that should be 4. If it's a cuboid, that should be 6. If it's a cuboid, there are 6, what do you call it, faces to that. But on this side, it is 0 because electric field is 0. And on the 4 other faces, the normal vector is always perpendicular to the electric field, or I can choose them to be perpendicular to that. Best is to take it as a cylinder, that way it is very clear. And that's gone, so there's only one face left that survives, and that's that face. That's z equal to 0 plus delta. So exactly what you point out. Okay. And that's primarily because of the divergence theorem that we can isolate it at one place. And that's a basic idea we will choose again and again. That force integrated right away, choose an appropriate volume, and this can be evaluated on a surface. That's the basic idea. And that's where that piece comes, that who says it should be 0 plus delta? Should be able to do this and do the same thing. It seems like delta doesn't really matter where I choose my delta. Okay, so that's something you learn, that, oh yeah, whatever is the force, it doesn't matter whether I hug the plate or actually take a bigger region of space. So it seems like the whole space is getting full. Right? That's not a very normal concept we think of, right? I mean, I'm just trying to interpret, and you don't say that a force is pulling a whole region of space. You only say material, right? So, but here the interpretation is that there is a stress on a medium. This whole medium is getting stressed. There's a stress on that. So, in this case, it is all flat, so it is not significant. But if you take it as a sphere, you're saying that there is a whole stress on a medium. Even without this positive charge, you can say there is a stress on that. But of course, always it will end on a positive charge. Okay, is that clear what I'm trying to point out? Like that's why the section title, I say this is a stress on a medium, not necessarily stress on a charge. We usually say on a charge, right? Force on a charge, right? But here now you're saying this volume could have been extended and the whole medium is being stressed. Like there is an electric field at this point. And if that electric field there is an imbalance between this point and this point, there is a stress on this whole medium, which is necessarily, it doesn't necessarily have to be that there are positive charges. Just because of concentration of electric field, you could have a stress. A bigger, a nicer concept, I think, which you can extend this somewhere else is that, for example, like all this stuff here. So you can say, so this is a plate, right? So this is a positive charge. So the same capacitor, right? Negative, negative, and there's the electric field, and that agreed. And now let's say where is the and let's say there's gravity. This is under gravity. G. If I were to drop this capacitor under gravity, it will fall. Right? And I'm saying that there is mass m1, let's say, and this is mass m2. They will fall, they have to fall. There's a mass in there. Now notice, so force due to, so this is the mass times acceleration, let's say, is m1g plus m2g. But we just now said that there is electric field in between the two plates. If there is an electric field, there is an energy between the two plates, half epsilon E squared. If there is an energy using Einstein's principle, it acts like a mass. So this electric field experiences gravity. Right? That will also fall. So this is not a complete statement. There is an additional force, which is energy is equal to mc squared, where energy, electromagnetic energy now, right? So it is E due to EM, let's say, or U, right? Best is to write U, right? U due to the electromagnetic energy over C squared times G. That's necessary if relativity is correct. And this has been, this was said right after, I think even before Einstein's, no, because speed of light probably at that same time. And there are experiments that have been done, and this works. Right? This is the equivalence principle requires this to work. And why did I say that? Why did I bring that up? It's just like, you know, what was the point I was making? Yeah. Yeah, okay, so it's just energy. But it's a good point to make. Okay, so we are talking about this force. Or we want to calculate that. Like I was not answering, I was not trying to answer any of your questions, right? Did I answer your questions? I don't know why I started this discussion. Okay, so we are calculating a force on this plate, and that's force per unit area. It turns out is sufficient, and that's given by calculating this. So that means that I just have to calculate the stress tensor at this point, which seems to be, I know the electric field. Like it seems like I should be able to do that. So let's start calculating that.
The stress on the medium.
Yeah. I was trying to say that, yes, there was a stress on the medium, and then I wanted to convince of what does it mean by stress on a medium. It may not be very convincing that actually this small volume where there is no matter, this can experience a force, right? That's not, that might be, you might suspect that, is this really true that a vacuum out there in space, it actually feels a force? There is nothing in it. No, it experiences force because this experiences a force. Right? This region inside has a force because there is energy in it. If there is energy, there will gravity will act on it. And just because there is electric field, there is energy. In fact, just because there is gravity, there is energy. Like just because of the gravitational field, there is energy. Right? And this is the idea that when you say there is you're aware that our universe is expanding, right? That's Hubble's law. That was already surprising in 1930s and 40s. It was realized that all the stars are moving away from us, and the conclusion was that our universe is expanding. That was surprising enough, but then you said that, oh yeah, there's an expanding experiment tells us that that's okay, we accept that. But more recently, in the last 20 years, there was a bigger surprise. And what was that? Regarding the expansion of universe?
Slowing down.
Yeah, not slowing down, it's speeding up.
Speeding up.
So it turns out, okay, it is expanding, but then this expansion is speeding up. And why is that such a big deal? And typically I explain it the following way. So there is some Big Bang, right? There's a lot of matter. Like think of a lot of matter put together. There is a Big Bang. Like whatever is a force, don't worry about what it is. So let's make it very simple. And I said, let's pick two masses out of this, right? So there is two masses, M1 and M2. A Big Bang is equivalent to, so there is a spring here. And these three are three separate masses, right? So there is M, and there is a mass of the spring also, right? But these are disconnected. Now I push them together. Whatever the spring is equivalent to our gravity, a gravitational interaction or pressure, basically. Just because you push each other, no, you push back, right? That's what it is. Now you push together, and then you release it. And there is gravity acting. That is the only thing you want to have, or whatever you know. Right? There's gravity, electromagnetic, strong, weak. That's the only four forces we know. All forces are acting on this. Now it moves here, right? It has reached here, and it is moving away. That's great. But how can this accelerate? Whatever you do, this will pull it back, right? Gravity, whatever, how much ever slow it is, but it will pull it back. If it is electromagnetic, we know that our universe is neutral, so we don't expect that this is a positive charge, that's a positive charge. We don't see galaxies that are charged, right? But it turns out that every star that you say, it's not only moving away, it is accelerating. It's getting faster and faster. And there is no way of explaining this. And if you want to make it very dramatic, it's kind of an embarrassment that we don't have any hint of why that is happening. And this is an open question for, I think, about 70 years or something. Like many clever people have addressed this, and there is no hint of why that is happening. Absolutely no hint. And then you say that, oh, okay, that's so in that, then you say that, oh, but there is electric field in here. Like there is a region of space that is full of electric field or gravitational field. There is a lot of, you don't need matter as such. So the whole region of the whole space of our universe itself has an energy. And then you ask, okay, what is the pressure associated with that? And it turns out that vacuum energy, that's what we call vacuum energy, that can be negative, that can have negative pressure. So which was very promising. Oh, that's good. So you can have negative pressure associated just because of fluctuations in electric field. You're not saying electric field itself, because electric field doesn't exist in that region, but there are fluctuations in that electric field. Like that means quantum fluctuation. It's not zero, it could be zero plus or minus, right? It's like temperature fluctuation these ways. And that's great. So you put in that, but then you calculate that pressure. One would expect that you should be able to explain this acceleration. And that calculation is off by about more than 100, I think it's 113 magnitude, right? That's kind of no way it can be, or at least in the naive way when you calculate it, it doesn't account for it. So my point is that that's the closest one can get that, yeah, there is a vacuum energy which can actually attract, but it doesn't explain it. And as of today, there is no hint of what this is. And if it is there, like about probably 70 to 80% of whatever we see is that. So it's sort of, one can dramatize it by saying that it's an embarrassment for all the all of us as scientists that, okay, we don't have any ideas, we're out of ideas. So young people, you guys should think out of the box. Like that's a place where to think out of the box. Right? Relativity came and like everyone was thinking the same way, and relativity came and that's you should think like that, and everything changes. The quantum mechanics came. So these are the times when big things happen. But everyone tries, but it's not been very successful. Yeah. Okay. So that. So okay, I should finish this problem. Okay. So this is force. Let's calculate the force. Pressure actually, right? Force per unit area, that's the pressure if you want. Directional pressure if you want. That's minus we have dotted with t. It's a vector. It's a tensor, but one of them contracted does give you a vector. So this is z equal to 0. Plus delta. What is t? T is equal to 1 times. First, let me calculate u maybe, right? Let's calculate u because t involves u. Right? So let's calculate u. It is half d dot with e plus half b dot with h. We are calculating u at. So this is u is a function of z in principle. So we are calculating this at z equal to 0 plus delta. That's equal to this is 0 because b is equal to 0. That's half epsilon naught e squared e dot e at z equal to 0 plus delta. Electric field we said is that right, sigma over epsilon naught. So this is z dotted with z, that's 1/2 epsilon naught, and this is sigma over epsilon naught, and that is sigma over epsilon naught. So it's basically half sigma square over epsilon. That's just giving an expression in terms of the quantities. Basically, half epsilon e squared is the best way. Typically, when you say how much energy is there in a capacitor, you say half epsilon e squared. E becomes the more unifying. But if you want it in terms of charges, then it's okay. So that's your u. But we are interested in t, right? That's what gives you the force. Then you have t. We have to calculate it at c equal to delta. So this is 1 times u. U we know, and then this is minus t times e. This time, no dot product, and that is b and h all goes to 0. Right? So this is equal to 1 times u. I'll write it as u itself, the half epsilon squared, and this is minus of epsilon times e. And that is a z hat, and this also has a z hat, and that's a way of writing. That way I can combine the magnitudes together. And this is 1 u minus epsilon e squared, half of that is u. So this is twice that. So this is 2 times u times z hat. That's your t. And I cannot simplify this further. Remember that it helps to recognize that 1 is equal to x hat plus y hat plus z hat. Right? It's a diagonal element of a matrix. Only 3 of them survive. So that's important. So this doesn't come. There is an x hat, but there is no. So there's a asymmetry in the diagonal terms. There is x hat is 1, y hat is 1, and z hat is minus 1, right? 1 minus 1. So that's what it is. But let's oops, I missed that. So let's use z hat times t, right? That's what we want to do. So z hat dotted with t is equal to z hat dotted with 1, which is z hat dotted with 1 with it, times u minus 2 times u z hat dotted with z hat. But because that's what gives me my force. This is z hat itself. So u times z hat minus 2 times u times z hat, and that's equal to minus u and z hat. So the force per unit area on the left plate, that is the force on the right plate will be negative of that. Force on the right plate or left one, right? This one, right? Is minus of this quantity, so it's plus v hat times u, which comes out correctly. U is a positive quantity plus where u itself is half epsilon naught v squared, positive quantity. So the force is in the positive z direction, and it's exactly equal to the energy density, force per unit area. That suspects of force, how is the force equal to energy, right? But remember, this is energy density, energy per unit volume, and this is force per unit area. Is that dimensionally correct? Energy density and force per unit area. So let's see, energy, force times distance is energy, right? So and energy, this is energy per unit volume. Energy is force times distance. Force times distance divided by a volume, which in fact gives you force per unit area. Force times distance and volume, that's force over area. So U is force per unit area dimensionally. That's correct. So energy per unit volume is that, and that's it. I mean, we can do this using charges also, and it gives exactly the same relation. So we have calculated the force on a parallel plate capacitor, one of the simplest problems, and calculated the force on a medium instead of actually the plate itself. Any questions on this? Yes.
So when dotting the stress tensor with like a C hat, X hat, or Y hat, we just pick out the column.
Maybe I didn't understand.
Like when we do that, we just pick out the like, because I'm thinking of it in terms of like a matrix.
Yes. In terms of a matrix. Yeah, okay. So matrix interpretation helps in index notation.
Mm-hmm.
So how you want to see that is, yeah. So think of it here as T ij. That's this equation I'm writing, right? And that's equal to del ij u, and minus this contributes only on z hat, right? So this is minus 2 times u times del 3. If you want, so there's an I. So how do I write this? How can I write this? So maybe 0, 0, 0. So that's that matrix interpretation there. Does that help? Maybe. So this is u times 1, 0, 0, 0, 1, 0 minus 2 times u times 0. Was it? And that's where I said we had. And, yeah, so this is a dyadic notation. It has the same information, but here we can use vector ideas. Is right. And I like this one better because this is okay in rectangular coordinates. There is a one-to-one correspondence here. This is very straightforward. But very soon I'm now going to do a sphere. I'll do a spherically charged sphere, and again ask what's a force, like a single sphere, and then this like what is R component, reading that out is a little more tricky. There is a little more work to be done, and this way of doing it takes immediately. Questions? But do you see the difference in the interpretations? I think I'm trying to emphasize on that a lot. We are talking in terms of fields here instead of charges. Like elementary physics does it using charges. Electric field doesn't play an important role. We do it in one small section. If I take the standard textbooks, we take a small section where you say that what is the energy density of the capacitor, and you do calculate half epsilon E squared. We do calculate that, but that's in a small section at the end of the chapter, after the fourth chapter or something. So here it is. That's the central piece, no charges.
Why you are emphasizing that you are using field? I mean, because of using substitution.
Oh, yeah. I mean, it's a different, like if I'm doing radiation pressure, like, yeah, why am I emphasizing? Good point. I'm just trying to point out that this is a different, I'm not saying this is more powerful or anything. I'm not trying to say that this is, in fact, this is a failure in the sense that there are inconsistencies in this, right? So in that sense, it is a failure. But this makes contact with the physics that we do much better than when you do charges. Here, there is a momentum, there is a force, everything seems to be all familiar idea. And in that sense, it is more intuitive if you want. And these all equations are all okay. As far as you're not in a medium, there is no problem. If you're in a medium, there are inconsistencies. And in fact, that is what, again, historically, it is beautiful in the sense of Lawrence was the idea that we should emphasize on this, and he was the authority, and everyone was working on that. He had Lorentz transformations named after him, but he was so occupied with the idea. This is called the electron model. At that time, it was called the model of an electron. So he was so occupied with this whole idea that he did not see relativity, which was right in his hands. So it's a preoccupation, yeah. So why emphasize it? Because it is still useful. It's a different approach.
The new concept here is, I mean, there is stress in the medium.
Correct, exactly. That's all. Or more importantly, a vacuum region that does not have matter, the region that does not have charge, does not mean that it's empty. It has energy and momentum. That's, I mean, electric field has energy and momentum in principle. There is magnetic field also, which we don't tend to emphasize so much in our understanding. Right? When I say a charge is there, the charge moves, I understand what a momentum is. But a charge moves with its field, right? And that field has energy and momentum in it, and we don't emphasize. It is there, and everyone does it. I'm not trying to say that it's only I'm doing it. It's just we tend to miss it in the way we emphasize our electromagnetic ideas. We tend to miss that, miss to emphasize that there is energy.
I mean, that's how it relates to the expansion of the universe.
That probably is how it relates to it. Yeah, that is an additional thing I'm writing as to motivate you guys. Yeah, that's probably how it does it. But But it seems like it doesn't. It's something else. Yeah, it strongly seems like that is something.
And it makes sense. I mean, when you go upper to the outer range, where there is a medium sometimes. So
Yeah, exactly. So what is that? The gravity is there. So that means there is energy, is there, right? Gravitational waves, right? There is energy there. But still, we are not able to account for the energy, missing energy. So that's the dark energy. Yeah. Yes.
Can you measure the stress tensor? Is it like a measurable quantity?
Yes. So, for example, this, right, I mean, again, it has to act on something. So in that sense, when you say radiation pressure, yeah, it will always act on something, right? Otherwise, how can I measure that? No, it is okay. That's where this interpretation came in, right? If I were to drop this, and if the acceleration has this extra piece, isn't that convincing enough that there is energy there, there is pressure, and correct? It is resisting it or it is increasing. In fact, if that's a beautiful part. So here it is no problem because this is a positive quantity just now I said, right? So everything is falling, there is energy in here, everything is falling. No surprise there. But now let's say this is not having charged plate. So this is not a charged plate anymore. So this is a neutral plate. So two conducting plates. So charge is Q is equal to 0 here, Q is equal to 0 here, right? So one, okay. Yeah, so now it is a neutral, two plates. There is no electric field probably here, right? But now this is a conductor because of fluctuations in, so then you say, where does fluctuation come in? I am going to put T equal to 0. That's a temperature equal to 0. So where are the fluctuations? But that's where quantum fluctuations come in. At quantum level, there are charges created and destroyed all the time. So you cannot avoid that. So there are fluctuations all the time. So that will disturb this. So this will polarize this plate. If this polarizes, it gets polarized. So effectively, there is an interaction, right? And that interaction, so now the idea is that electric field is 0. In what sense? Average of the electric field is 0. But average of the electric field 0 does not mean square of the electric field is 0. E times E, that does not mean that. You can have a E equal to 0, but square is not 0. Is that clear? Take 5 numbers, sum of them is 0, but the square of them will not be 0. Like variance is not 0. That's not equal to 0. That's possible, right? If this is not 0, energy is not 0. So even though there is no electric field on an average, there is energy between that plate. Correct? That's vacuum energy. Neutral plates, right? Neutral universe. But there are quantum fluctuations which have a vacuum energy. Is that clear? Right? So great. So once we accept that, so now we have two plates. Again, M1, M2, and now there is vacuum energy, right? So this is what we call it vacuum energy, V. Right. So that's right. So again, you would say that, right? So mg or a mass times acceleration is equal to m1 plus m2 plus u of ve times g. Right? That's how it should be. The surprise here is that this energy is not positive; it's negative. This vacuum energy between these two plates that's measured, this is what is called Casimir effect. So that's negative. This is negative. E means negative. That's negative. That means these two plates, when they fall, they will, because they have energy, they slightly have a buoyancy. Like this is going to resist the fall. This is like a negative mass. And that's why that negative mass is what motivates you to, oh, that's what is probably accelerating. But it doesn't explain it. one has done this calculation and it doesn't expand. But that's the negative piece in there, so it's kind of beautiful. Today I'm forgetting the continuity of the argument here. Okay. Oh, yeah, what are we going to do next, right? So that's good to know. So we'll do let's say if I were to ask you that there is a positively charged conducting sphere, uniformly positively charged conducting sphere. And is there a pressure on this? Right? If you were to calculate, like all these positive charges want to be away, right? They want to be away from each other. So there should be a stress. They should try to repel each other, and this should try to grow in size, right? That should be a repulsive force, and that should be possible to do. But now try to calculate that using your charge expressions, and suddenly there might, I mean, it actually cancels out, but naively speaking, you would say that, oh, then I want a repulsion between this point charge and right next to that. But two charges, when they go very close to each other, they diverge, right? 1 over r diverges. Right? So it seems like, oh, how do I calculate this when there is a divergence? But actually, they all cancel out, and there is a nice answer in that. And we will do that using this expression and get a very neat expression. So even for a single circuit, so think of a pressure associated, which is intuitively clear. So we'll calculate that stress on it. And what you will do in your homework is that, so now suppose you have a positive charge and a negative charge, right? We know Coulomb's law very clearly, right? Well, the force on the positive charge is Q1, Q2 over the distance between them, that's a square. Right? And that's a 4, 5. Oh, again. Oh, is that right? Yeah. Yeah, sorry. Is that clear? Yeah. So here, so this is Q1, Q2 times a square, right? That's 1 over 4 pi epsilon naught. And if I say this is my z direction, this will be attractive, so that will be z hat. Right? That's my force. Okay. So, but I want to not use Coulomb's law, I want to derive Coulomb's law. But the understanding is that I know the electric field due to these two charges. Right? So what I'll do is again have a volume, right, around this. Right? So integrate over this region and again make it small, like make it hug the positive charge. That in this case it was not very powerful, but in this case it will be very useful. Because then we can actually make the approximation that it is so small, I can do a series expansion. So in your homework problem, you will calculate the force on this and get exactly this result. Is that clear, the motivation? But then you would say, okay, why make this surface here? What if I actually do another calculation, which is also part of your homework? That's the last part in the question, that there's a positive charge and a negative charge. This time, don't calculate the force on this, but have a whole median. Split the space into two, and the whole volume, your volume is going to be this. Even though the charge is down here, the electric field is there. Right? And calculate the force on this volume. Everywhere else it is 0 because it's at infinity. So calculate the force here. And on this wall, calculate all the electric field, and again do it again, it will come out to be exactly the force Q1, Q2, because this whole volume acts like a single point charge. That's what it is pulling, right? But this time it is the electric field that is contributing to it. Is that clear? What I roughly said? Okay, so here there's a positive charge and a negative charge, right? I chose, it's all about choosing the volume, right? I choose the volume to be enclosed in the sphere and I made it small. This time I don't make it small. My volume is this whole volume V. That shaded region is my volume V. And I again calculate my, let's say, del dotted with T on that EQB. But this volume, right? This is immediately on this, correct? And now what are the regions? There is a boundary there, but that's at infinity. Electric field goes to 0 at infinity. There is an infinity here, it is 0. This also goes to infinity, that is 0, because the electric field dies off, right, for a point charge. So there's only one surface remaining. So I just have to do, instead of this, so this is the same as this surface, which is the A, let's say, and its n is in this direction, so that's z hat, dotted with T. This time evaluate it at z equal to whatever this position is, that's at 0. So same idea comes in, but now T will be different. The T there was for a capacitor, here is for 2 point charges. And again do the calculation, and it immediately comes out. It's just the expression for E, which is small here, that changes, and you put it into T and evaluate it on the boundary. That's the basic idea. Clear? Yeah, let's see how we present it. Feel free to ask questions. Yeah, maybe yeah. Go ahead.
I'm just kind of curious, like previously in E&M, we would make like Gaussian surfaces.
Yes.
Is this kind of similar?
Same
to like a
thing,
stress
same-
kind of
same.
volume?
Yeah, but now it is the stress that is being
Right.
calculated.
Okay.
There it used to be electric field. Here it is a T. This here it is T. That is the vector, which is a tensor. Basically. There it was a vector. Now it's a tensor being evaluated on the surface. That's all. Yes.
Interesting. Okay. So in choosing the actual volume.
Is you have to be clever about that.
Okay. Okay.
Or you can say that you can deduce various things by choosing different volumes.
Right.
If 2 different volumes have the same answer, then you're saying that this is equal to that, which can be more information about the system.
Thank you.
Okay. Are you guys familiar about potpourri seminar in the math department?